Okay, and we're live. So you should be able to hear me. And if you can hear me, give me a thumbs up so then we can get started. Um, okay, excellent. So, E2, do you want a plant? Well, I walk around and I place plants whenever I hear people talking when I stop by in their room. Obviously, I can't be everywhere at the same time, so not everyone may get plants right away. But some others apparently have already a couple of plants and a stained glass window and garlands and all that. So um, just give it time and you'll find that things appear in your rooms when you discuss. So excellent. I think some of you are a little bit on a delayed stream today because I see the reactions coming in with a little bit more delay than it was in the last couple of weeks, last couple of lectures. Okay, so let's get started. Today we're going to be talking about motion in 2 and 3 dimensions. So in particular, we're going to be talking about kinematics. So just as a reminder, kinematics, again, this is the study of motion without regards as to how it is being created, just describing the motion itself, velocity, acceleration, displacement, position, all of those good things. We'll start in next week's lectures. We'll start talking about dynamics, which is about how that motion is created. So what forces are causing motion, and in particular, how does the kinematics follow from the dynamics from the forces that are applied. So we've talked about one-dimensional kinematics, so motion along a straight line, and so now we're going to be talking about 2 and 3-dimensional kinematics. Now it's going to be easy. Motion in 3 dimensions is essentially 3 times motion in 1 dimension. One of the great benefits of kinematics is that we can actually treat the motion in the 3 dimensions, in the 3 directions, x, y, and z, as independent motions. So if something is accelerating in the x direction, it will not be, if something is accelerating with an acceleration vector only in the x direction, with 0 acceleration in the y direction and 0 acceleration in the z direction, then there will indeed be no effect of that acceleration in the x direction on the position or the velocity in the y and the z direction. So let's introduce that a little bit more mathematically by looking at positions first in 3 dimensions. And of course, we're going to be talking mainly about 3 dimensions, but it should be straightforward to simplify that again to 2 dimensions. So if we're talking about 3 dimensions, we have x, y, and z. If we're going back to 2 dimensions, we'd typically be only talking about x and y, and actually oftentimes we'll be talking about x then as the horizontal axis and y as the vertical upward axis. So if we wanted to draw this in 3 dimensions, we'd have z as the vertical upward axis, y here, and x here. In 2 dimensions, we'll often see y in this direction and x in that direction. Now, of course, everything is still valid, right? Okay. So if we're talking about a position, so the position will change with respect to time. So the x, the y, and the z coordinate, the x, y, and z positions will be functions of the time. And with those x, y, and z positions, we can create a vector from the origin of our chosen coordinate system to the point where our object or particle or projectile is. And that will now be a vector that is time dependent. So the vector is a function of the time. This is a vector that is specific to the choice of the coordinate system. So if we choose a different coordinate system, we will, in particular, if we choose a different origin, we will find different vectors, right? So in some sense, this corresponds to what we call the scalar quantity before. The reason why this is a vector now is because we're working in 3 dimensions. This is a little bit different than the next vector we're going to be talking about. That's the displacement vector. The displacement vector is when we have a displacement from one position, P1, to a position P2. This one is position R at time 1, position R at time 2. So the individual positions depend on the choice of the origin, but the actual difference between the positions, which is what the displacement is, it's the R2 minus R1, or R at times 2 minus R at times 1, that will actually not depend on the origin. That vector will be the same regardless whether we pick the origin here or we pick the origin there, or even somewhere else entirely. So one of the advantages will be to pick the origin so that our positions are going to be easy, and in particular so that our positions are going to be 0, or positions are going to be along one of the major coordinate axes. The motion is going to be along one of the major coordinate axes. And our displacement doesn't actually depend on that. So we have our position vectors, r as a function of t, and now we have a displacement vector, delta r of t. So the xyz orientation is not fixed in 3 dimensions in the sense that we can rotate this whole set of 3 axes, but we always want to maintain right angles between xy, yz, and between zx, and we want to also maintain a right-handed coordinate system. So don't change x for y and y for x, because that would leave you with a left-handed coordinate system. So you have to be able to put your thumb of the right hand in particular in the direction of the x-axis, your index finger along the y-axis, and your middle finger should then be pointing in the z direction. So from position to displacement, of course the next step is going to be displacement along a path that a particle is traveling along. And I should point out here, when I'm talking about particles, so partly of course it's because I'm a particle physicist, subatomic physicist, but that's not actually the reason why we're using this terminology. We're using the terminology of particle whenever we're talking about something that we can approximate as having all of its mass, all of its everything that defines its kinematics in a single point. So a particle or a point is another term that we'll use, or a projectile, as we're going to talk about. Those are terms that we use here. So a particle would be, for example, a baseball. You need some skill to throw a baseball this way, but a particle would be moving this way, and so we can look again at position at some time later, and there will be a displacement between time t and time t plus delta t. And if we of course make delta t smaller and smaller and smaller, this is going to be pointing along the tangential direction to this trajectory that the particle describes, or the path of this particle. Now if we have this displacement at a very short time delta t, then of course the next step will be to turn that into a velocity, just like we did in uniform motion in a single direction. And I'm actually not putting the formula here, but of course if we go from position r as a function of time to displacement delta r, again a vector as a function of time, then we can go to, let's call it first instantaneous velocity. So that's going to be v as a function of time, which is the limit of delta r over delta t, or the derivative d dt of r as a function of time. Okay. Similarly, there's of course going to be average velocity. So that's going to be v average, which is now just delta r. I'm not going to put t here because it's delta r over delta t. And of course delta r will be delta r at times t plus delta t minus delta r at times t over delta t. So then that allows you to take that limit here, and I should specify the limit is, of course, for delta t going to 0. So all of this is very similar as what we've seen before in one dimension. The only difference might be that here our vector v is the derivative of a vector. Now the derivative of a vector, if this is d dt of r of t, that is just a vector that has it as the x component dx dt, as the y component dy dt, and as the z component dz dt, right? So you can just do the derivative to the time on a on an individual component level. Or the other way to write this is, of course, dx dt times x hat plus dy dt times y hat plus dz dt times z hat. So there's nothing special about derivatives of vectors, type derivatives of vectors. All it does is taking the derivatives component-wise. So let's look at an example here. Let's just look at an example where we are given the position of a particle that is 3.0 times the time to the third power in the x direction plus 4.0 times in the y direction, and all of this is going to be in units of meters. So we could ask, what is our instantaneous velocity at t equals 3.0 seconds? So how would you calculate that? And for those of you who haven't gotten calculus yet, or may need a refresher, the derivative of a function that looks like a constant times t to the power n will be n times that constant times t to the power n minus 1. So this is going to be the formula to use to evaluate that time derivative here. And if this looks weird to you, no worries, you'll be covering that pretty soon in calculus. So what is the velocity, instantaneous velocity at time t equal 3 seconds? So how would we solve that? So I'll let you all think about that for about a minute. So go through the math that is needed, if there is any math needed, and then plug in the number. Okay, so let's see what's our derivative at a general time t. So that will be the first derivative to the time of this expression here. So let's look at the x component. We take the derivative for the x component separately as a derivative for the y component. So for the x component, we see that we've got 3 times t to the third. So if we use our formula here, that derivative becomes 9, because we place our exponent in front, multiply with 3, and then we have t to the power 2 left, and this is going to be in the x direction. And then now here we have our factor 4, a constant, which really is t to the 0, right? If that's t to the 0, there's no time dependence here, and we put 0 in front and multiply with 0, we'll find 0. So there's no y component to the velocity. The velocity is entirely in the x direction. And so now when we plug in t is 3.0 seconds, that will be 9.0 times 3.0 squared. I forgot my direction here. It's a vector, always specify the direction. And it's physics, so always specify units. So this will be 81.0 meters per second in the x direction. It's not really that important to whether you put the x before the units or after the units. As you see, I've done this here in different ways. Here I've placed x after the units. Here I've put the units after x. The reason why I place the units after x in the position is because then it applies to both terms here. In this case, I only had one term, so there's not really any benefit to writing it differently. So that's our average velocity at t equals 3 seconds. How does that compare to our average? This is our instantaneous velocity. So how does that compare to our average velocity between 2.0 seconds and 4.0 seconds? So there's two ways we can go about that. One of them would be calculating delta r first, which will be r at r at 4 seconds, 4.0 seconds, minus r at 2.0 seconds, and that will be a vector, and then we have to divide it by the time interval delta t, which in this case is of course 2.0 seconds. So if we calculate this delta r, we'll get an x component, so we'll get 3 times 4 to the third power minus 3 times 2 to the third power. That's going to be our x component. And our y component, we'll get the same thing again. So 4 for the first one and 4 for the second one. So we'll end up with no y component. For the x component, we'll get 3.0, 4.0 to the third power minus 3.0 times 2.0 to the fourth power. And if you plug in the numbers, you'll see that that gives us delta r. And so all of this is in the x direction in units of meters. So delta r will be 3 times 4 to the third power. You'll plug that into your calculator or do the math in your head, and you'll find 84 meters in the x direction. Actually, you'll find 2 times that, 168 meters. And then when you calculate v average, that's delta r over delta t. That's going to be 168 divided by 2, and that is 84 now in meters per second in the x direction. So if we compare that, we see that the average velocity is 84 meters per second in the x direction. The instantaneous velocity is different, and so that's of course because this time dependence doesn't result in the velocity, the instantaneous velocity, being exactly the same as the average velocity. That would only be the case if there's no acceleration. Okay. Any questions about this at this point? I think we've got a little bit of a lag on the stream, so I don't necessarily see the questions right when you're asking them. If you get this, if you hear me saying this, just give me a thumbs up so I can see how many of you are actually synchronized, and how many of you are still a little bit behind. Okay, I see at least several of you are fairly well timed in. Oh, excellent. Okay, so we've calculated now in 3 dimensions the velocity, and we know how to do that based on a functional description of the position. So now, of course, we're going to want to do that again for getting from velocity to acceleration as well, right? So one question here was, how do we get to this delta r? So delta r is r at 4 seconds minus r at 2 seconds. And because the y components will be the same for r at 4 seconds and r at 2 seconds, we're not going to have a y component in the difference. I realized that I have a power 4, which should have been a power 3 here. So that's going to be 3 times t to the third, so 3 times 4 seconds to the third, minus 3 times 2 seconds to the third. Now t is equal to 2. So that gives us that difference. And so if you plug in the math, 3 times 64 minus 3 times 8, that will give you 168. Okay, so let's go back to the slides here. I do want to go to these formulas. So we've covered now positions in x, y, and z coordinates, differences in positions, which are displacement vectors, and the velocity vector as the limit of the displacement over the time. The velocity can again be composed or decomposed in 3 different components: the x velocity, the y velocity, and the z velocity. Each of them are individually the time derivatives of the x, y, and z positions. So that gives us these formulas. And then, of course, the average velocity is the displacement between time 2 and time 1, or time 1 and time 2, over the elapsed time between time 1 and time 2. Now, the same thing is true, of course, for the acceleration. So for acceleration, this will be the limit of the velocity at time t plus delta t minus the velocity at times t over delta t. So that's the derivative of v, of the velocity vector to the time. And again, the acceleration will have an x component, a y component, and a z component. And each of those components individually will be the derivatives of the corresponding velocity components, vx, vy, and vz. So of course, a relates to v as v relates to r, and so on. We can also, of course, do the derivative, the double derivative here. If the x component of the acceleration is the derivative of the x component of the velocity, then the x component of the acceleration will also be the second derivative of the x component of the position. So yeah, if you haven't seen calculus yet, then this will make a lot more sense pretty soon. But that's why it's a co-requisite for this course, right? The important part really at this point is mainly going to be this formula. That's the only calculus formula that you need to know right now, and that's how to take that single derivative. Everything else, you can just focus on the formulas that we've used, which are remaining the same in 3 dimensions, because we can treat everything separately. And those are going to be, for example, x is x0 plus v0 x times t plus 1/2 ax times squared. And similarly for y, we'll get y0 plus v0 y t plus 1/2 ay t squared. And I'm not going to write the same thing for z. So that's one formula that now became 3 formulas. We'll have vx is v0 x plus ax times the time. Vy is v0 y plus the acceleration in the y direction times the time. And the same thing for z. And then finally, there was vx squared is v0 x squared plus 2ax minus x0. And this is now the acceleration in the x direction. Vy squared is v0 y squared plus 2ay not x y minus y0. And the same thing for vz squared. So these are now the main formulas. If you don't, if you haven't seen calculus, then these are the formulas you'll want to focus on right now, because they do everything right, of course, for constant acceleration. And in some sense, this one, we can even combine these and write that r is r0 plus v0 times the time plus 1/2 a times time squared. So that's introducing this as vectors. We can do the same thing with this one. We can write this as v is v0 plus a times the time. Unfortunately, we can't really do it with this formula because it involves the squares, and so we're not necessarily looking at vector quantities where we can write vector equations for anymore. Okay, let's look at an example, or let's look at how this is actually used. So you can kind of see that in these formulas for acceleration, the x component of the acceleration only involves the x position or the x velocity. There's no mixing of x components with y components and z components. So the horizontal and vertical motion will actually be separate. If you let's say stand on a cliff and you do two things. You drop a ball, but at the same time you throw an equal ball. It doesn't even matter that it's an equal ball, just another ball. We'll talk later about why it doesn't matter what ball it is. But if you drop these two balls, one which you give some horizontal velocity, they'll actually fall in the same way if you consider just the y component. They'll fall at the same rate. So after a certain time, they'll be at the same y height. At another time, they'll be at the same y height again. They'll remain at the same height at all times, as they of course accelerate due to the free fall that is taking place here. The only thing that's different is the horizontal component. This ball that just falls down doesn't have a horizontal component to the velocity, so it doesn't move horizontally ever. There's nothing that introduces a horizontal component to the velocity, so it remains just falling straight down. The other ball, which you gave a horizontal component to the velocity, it does move to the right, and it remains moving to the right at that same horizontal velocity. Why does it move with that same constant velocity? Because there's no acceleration. There's nothing that provides acceleration to this ball in the horizontal direction. The only acceleration is in the vertical direction, and that's the acceleration due to free fall, the minus 9.8 meters per second squared. So that's the that indicates already that we can treat this horizontal motion independently from the vertical motion. And we'll be able to use that to great effect. So if we look at, for example, here a ball that now is launched at an angle upwards and then describes a trajectory or a path that looks like this, parabola, which we'll be able to derive that is indeed a parabola. The horizontal component of the velocity is always the same, remains the same, and it's given by the initial horizontal velocity that we gave to that particle when we launched it. The vertical velocity starts at an initial positive velocity, but there's a negative acceleration due to free fall, due to gravity again. And so it will decrease in magnitude. It will be 0 at the point when we're at the highest point here, and then it will increase in magnitude downwards as the ball is moving down. But we can treat this vertical velocity and position and acceleration entirely separate from the horizontal component. So that will be the benefit of these kind of systems, is that we can independently consider the horizontal and the vertical motion, which is of course also what we see in these formulas here. So let's look at an example. Let's look at this example here, a skier skiing down a slope. This is a problem that I'm sure we will see again later in the term. So we have a skier skiing down a slope. The slope is at 15 degrees, and we know, we're given that the skier has an acceleration of 2.1 meters per second squared. That is along the slope. So if that 2.1 meters per second squared is along the slope, how that acceleration came to be, we don't have to worry about right now. that is something for the next chapter. But let's assume that we know, that this acceleration is 2.1 meters per second. So how do we write down, and the other thing we know is the initial position at time 0 and the initial velocity at time 0. So let me write that down. So this is skier down a slope. So the acceleration is 2.1 meters per second squared at 15 degrees below the horizontal. Of course, we want to write this in x, y, and z components, and in this case just x and y components, because we can just treat everything in the plane of the page here, in the plane of the slide. So if there's a skier going down and the acceleration is pointing in this direction, what will be the sign of the x component of the acceleration? Will the x component be positive or negative? Yep, so I see several of you posting in the chat already. So indeed, the x component will be positive. What about the sign of the y component? Will the y component be positive or negative? Yep, and indeed, the y component will be negative because it's going to be pointing in the opposite direction as the y-axis that's drawn here. So if we want to turn A into x, y components, we'll find, well, let me just write AX. AX will be 2.1 meters per second squared times the cosine of that angle of 15 degrees, right? So that's going to be the cosine of that angle 15 degrees. That will give me the component of the acceleration that's in the x direction. Similarly for y, now we know it has a negative sign, so we're going to put our negative sign there, 2.1 meters per second squared, and now of course it will be the sine of 15 degrees. And if you plug in the numbers, you calculate the sine and the cosine here, you'll find of course that indeed this is a positive number, this is a negative number, as I've picked with the sign here, and I used the angles without any signs, so I wouldn't end up getting the wrong answer. So now let's add two more bits of information. Let's say that at time t equals 0, we know that the skier started at 75.0 meters in the x direction minus 50.0 meters in the y direction, and that the initial velocity at this time 0 that the skier had was 4.1 in the x direction and minus 1.1 in the y direction in meters per second. So what will now be the position at any time t greater than 0, at any time t after that time where we're given here. So we can of course go back to our formulas, which were that r, or which were that for individual motion in along one axis, x is x0 plus v0x times the time plus 1/2 ax t squared. So the same thing will be true here, except it will be true for both x and y independently. So the x component will be 75.0, which is our x0, minus or plus 4.1 times the time, that's our v0x, and then plus 1/2 times 2.1 meters per second squared times cosine 15 degrees, and this all times t squared. So that's going to be our x component. in meters. And then we'll have a y component, which is going to be minus 50 meters plus, no, minus 1.1 times the time, and then plus 1/2, but it's minus, so I'm going to leave it there as a minus, so 2.1 meters per second squared times the sine of 15 degrees times t squared in the y direction in units of meters. So starting from just knowing the acceleration, the magnitude of the acceleration, the direction of the acceleration, and the initial position and initial velocity, we can calculate now the position at any time at any time t, right? So that gives us now an expression that we can fill in any time t, a function where we can plug in t and find the position. And of course we can now go back and we can calculate dr dt, the velocity, which will give us the velocity, and indeed at time t equals 0 we should find exactly that initial velocity. We can calculate a at any time as the derivative of the velocity, and we should of course find exactly this acceleration that we started from. Okay. So recap, we can calculate, let's do a recap because these are really the most important formulas in this chapter. So we can calculate the positions x, y, and z independently. They'll give us independently the velocity in the x direction, the y direction, and the z direction, and that will give us independently the acceleration in the x, y, and z direction. So we can apply that to these kind of problems to predict, in a sense, what the position will be at a time t given acceleration and initial position and momentum. But we can also do other problems with that, and in particular an important class of problems is so-called projectile motion, where we have something that is launched, projected, thrown up into the air, and it describes an arc before it maybe reaches a certain height. Maybe we're asked to figure out what the highest point is. Maybe we're asked to figure out how far this football, for example, landed. So those are problems of so-called projectile motion. And they're really just a special class of problems in 2 dimensions where we use a specific acceleration vector. And the acceleration vector for these projectile motions will be such that the acceleration is only in the y direction, it is pointing down, and it is exactly 9.8 meters per second squared. So if we go back to our whiteboard here, then for projectile motion, A is always minus g times y, or minus 9.80 meters per second squared times y. So if we wanted to draw this, the acceleration vector is always in the negative direction. So that will give us, in the case of projectile motion, where we start with a certain initial velocity, which has an x component and a y component, this x component won't change, and so when our projectile lands here, we know it will still have the same v0x because ax is equal to 0. What will have changed is the v0y, right? Vy will change. At this point here, vy will be equal to 0. At this point, vy will be negative. Let's make it negative. You can probably guess what it will be. Vy will actually be exactly the opposite as Vy0. Because at this point, the Vy is pointing upwards. At this point, it will be the exact same value downwards. And of course, if the trajectory were to continue, then Vy becomes even larger in magnitude. So the magnitude of Vy would become larger. So now let's, the formulas are, of course, easy to write down. So the x direction, it will be just x0 plus v0x times the time, because ax is equal to 0, so we don't have to write the term in t squared. Y is y0 plus v0y times the time, and now minus 1/2 g times t squared. So that's going to be the new term here. So these are the formulas that describe projectile motion, and that we can use to solve essentially any problem in projectile motion. So let's start with that problem here. For example, we have a tennis player who hits a ball into the stands at 30 meters per second at an angle of 45 degrees. And the question is, at what time does the spectator here catch the ball when we know that the spectator is sitting 10 meters high above the ground? So let's start writing that down. So we'll have the value, the question really is, when is y 10 meters, right? So that will be, when is y 10 meters? Y will be 10 meters when this fan here catches the ball. Now let's write down what y also is. Y is also y0 plus v0y times the time minus 1/2 gt squared. Now if y is 10 meters, then we must have implicitly assumed that y is equal to 0. And we must have put our origin of our coordinate system right at the point where the player is throwing the ball into the stands, right? We know what v0y is. It's 30.0 meters per second times the sine of 45 degrees. And we can calculate this, right? We can calculate 1/2 g, but we don't know t. So ultimately, we end up with an equation. 10 meters is 30 meters per second times the sine of 45 degrees times the time minus 1/2 gt squared. And this is a quadratic equation, and I'm going to end with this here. It's a quadratic equation in t, so you know this will have two solutions, right? It turns out the solutions will be t is 0.54 seconds and t is 3.79 seconds. Now, why did we get two solutions? We were trying to find the time when the fan catches the ball here. Well, of course, there's another time when the ball is at 10 meters height, and that's when it's going up and passes the 10 meter mark here. So that will be at 0.54 seconds, and then when the ball comes back down, that will be at 3.79 seconds. And so the question of what time does it take for the ball to reach the fan is going to have the larger of those two answers, because the shorter one is when the ball is still going up and hasn't even reached its highest point yet. Okay, that is it for today. So we're definitely in the projectile motion questions now. We're looking at x and y motion in these problems, and so the x motion will have no acceleration. Y motion will have a negative 9.80 meters per second squared acceleration, and that's of course going to define how the motion is different in those problems. So we're going to continue that on Monday with calculating what the velocity is that the tennis ball has when it reaches the stands, and then calculating some more quantities for projectile motion. So see you all on Monday.